Okay, uh, we are going to start now. This is the second lecture. Can somebody tell if they can hear me?
Yes, sir, we can hear you.
The, can you guys hear me?
Yes, sir, we can hear you.
Okay, that's great. Okay, so what I'm going to do is we are going to resume from where we had left with a little bit of, you know, recalling what we studied last time. Last time we talked about the internet infrastructure, how the packets or the data gets from one machine to another machine. And today we are going to continue with that discussion with a little bit more information, how the data in packets goes from one machine to another machine via reservations, and what is the basic design philosophy behind the internet. Um, so I'm going to start sharing my slides now. Okay. So let's see. Participants, and I see the participants window here. Just this is great. Um, so basically, you guys should be able to see uh, the raise hand features just at the bottom of participants list. So if you click on participants and see the participants link, you should be able to see a raise hand option, and similarly some other options. So what we are trying to do is we're trying to make it a little bit more interactive. Um, so um, let's first talk about where we had left off. What are some of the basic design considerations for the internet? One of the most important design consideration, as we talked about last time, is the connectivity structure. um, how the end devices are connected to the switches and how the switches are connected to each other. So last time we considered several examples. One of the examples was how the devices in my office and the phone in my office, how is this phone and this laptop or desktop, they are connected to you guys, and we are communicating with each other. So basically, what these devices are doing is that they are directly communicating um, with the Wi-Fi access point, which is close to my office up in the on the roof, and that Wi-Fi access point, this communication is happening wirelessly. That access point is connected through a piece of wire with another switch on this floor, which is in the corridor, and that switch is then connected to another switch which is in the basement of the SSE building. And then that switch in the basement of the SSE building is then connected through an optical cable through another switch, to another switch which is in the library building where the IST is resided. And then the IST department, they have connectivity through a switch to the large ISPs from where they have gotten the service. So connectivity structure is very similar. Even if you are connected at home, so maybe at your home you are connected using your laptop or whatever device you are using to a Wi-Fi access point, and that Wi-Fi access point is connected to PTCL network or Cybernet's network, and their network is then connected to the whatever ISP LUMS is using, and then we have a physical path available between us, and that's how we are able to communicate. The physical paths, they still remain there even if we are not communicating with each other. It's just that when we want to use those physical paths, then we start using those physical paths. This is similar to we gave an example of road infrastructure. The roads in the country, they are available to you whether you use it or not use it. So, but whenever you want to go from, let's say, Lahore to Islamabad, the roads will be available to you. You can take one of the paths in going from Lahore to Islamabad. We have yet to figure out how that path will be taken by a car which is going from Lahore to Islamabad, which path you will take. There are multiple options. You can go through motorway, you can go through GT road, and maybe there can be other options. You can go from GT road up to Kalashakaku, and then from Kalashakaku you can go to motorway, or you can go somewhere on the motorway, and then from Kalashakaku you can come back to the GT road. Many different options that you can take. Similarly, on the internet, the data which is going from one machine to another machine also will have lots and lots of options, much more options than the road infrastructure, much more options. And the packets which are going from one machine to another machine, one after the other, these packets will have to take one of the paths which is available. We will talk in lot more detail about what path will be taken by a packet and how that path will be determined as we progress in the course. But at this moment, we have to understand that connectivity structure is extremely important for the internet to function. The other thing which is important is addressing. We need to know where we are going. So a packet which is originated from my device must know where it is going. So since there are many students who are logged in at this time, the audio that is being produced here through the microphone is packetized by this computer, and this packetized voice, packets one by one will be reaching you, and you are receiving these packets, all of you, simultaneously. So that means the packet that I send from here will get replicated somehow and will be receivable to you at your individual destinations. Now, it is very important that, if we look at all the participants, 25 participants at this time in the meeting, including myself. So there are perhaps 24 students and TAs. So that means there are 24 copies of these packets which will be received by you guys. Now, nobody else is not receiving these packets. Why? Because they are not participants of this particular meeting. And the reason that you are receiving that is because you have joined this meeting. And now these packets which are being sent from my side, they are reaching just you and not somebody else who is not in this meeting, is because these packets know that these packets have to reach to these specific destination. And how do we know about those destination? Addressing is the answer to that question. So all of you have an address, an IP address, to be specific, and that IP address is the one which is used by the packets to go from my machine to another machine. Now, from my machine, it will determine that there are 25 people in this meeting with their respective IP addresses. So this packet somehow will get replicated into 25 different packets, each packet destined for its own destination, and it will reach you. So addressing is extremely important. Even if you are in a one-to-one conversation on WhatsApp using your phone, the other party on the other side will have an address. The voice which is being produced at your phone and being packetized, digitized and packetized, these packets which are produced on your phone through WhatsApp network, they will also go to the destination, and they will use the destination address. Similarly, if they respond, they will be sending audio packets to you, audio data to you by using your address. So very, very important to understand that you have to have a connectivity structure, the road network, and you have to have addressing. So sending something from one place to another place, if a car is being driven from Lahore to Islamabad, it will reach the destination, but we need to know the address of the destination. And the addresses in the internet sense are called the IP addresses. IP addresses. These are 32-bit numbers, and the newer versions of IP addresses are 4 times as long as the old IPv4 addresses. Predominantly at the moment, most of the internet is still using the old addresses, which are 32-bit addresses. We'll talk about the addresses and structure of addresses a little bit more in maybe about 10-15 lectures. The third thing, which is the basic design consideration for the internet, is data forwarding. So this is the same thing that I described to you, that if a car is going from Lahore to Islamabad, which path it will take. Similarly, the same question arises in the case of network. If I'm sending a packet to you, what path it will take. So for example, from here to this wireless access point, there is only one path, okay? But after that, this access point, well, again, there is probably one path which is connected to the switch on this corridor. And then maybe there is only one path which is going to the basement of the SSE, another switch. And then maybe there is another 4 or 5 paths. There are 4 or 5 paths which may lead that switch through an optical fiber to the IST building. Which path it will take? How do you decide that? Data forwarding, that's the routing question. And we will answer that question as we progress in the course. Similarly, once it is on LUMS IST router, which is connected to multiple service providers, multiple ISPs or service providers as we call it. So multiple ISPs, which ISP should I take? PTCL is providing service to LUMS, HEC PERN network is providing service to LUMS, WorldCall is providing services to LUMS. Which ISP should I take to send my packets out of my network? So that decision is very important. And you might realize that you don't want to send the data and it might go into loops. There will be loops in the networks and it might go into loops. You want to make sure that the loops are avoided and data is forwarded all the way from source to destination, hopefully along the best path, for whatever definition of best is. We will clarify the definition of best when we progress in the course. Okay. So at this point, if there are any questions, I will be happy to answer that. There are not too many students, so we can probably take some questions. Raise your hand if you have a question. Okay, no questions. So we will move forward. So connectivity structure, addressing, and data forwarding. Oh, somebody has a question. G, please go ahead.
Sir, I just wanted to ask, like, can you just repeat the difference between connectivity and data forwarding?
Okay, so connectivity structure is basically the road network is equivalent to the road network that you have in the country. And data forwarding means that how do you decide, on what basis do you decide that if you are going from Lahore to Islamabad, which path you will take? Okay, so the connectivity structure is the road network and data forwarding is the basis on which you will take the decision. Maybe you want to reach Islamabad very quickly, and it is okay if the path is slightly longer. So you will probably take motorway. If you want to go to Islamabad on the shortest path, maybe you will take the GT road. So that decision making is basically equivalent to data forwarding, and the connectivity structure is the road network. Okay, does that make sense?
Yes, sir. Thank you.
Okay, so then the next important consideration for the designing of the internet is the common language or protocol. See, the job of the internet is to make sure that two devices any two devices on the internet, billions of devices on the internet, any two of those are able to talk to each other, any two of those. So that means that these two devices which are willing to talk to each other, they must use the same language. They must understand each other. They must be able to talk to each other, understand what the other device is saying. So that is governed by what we call a protocol. And last time we gave an example that HTTP is a protocol. You send a web request to CNN server, your browser understands the HTTP protocol, and the web server, which is hosted by CNN, also understands the same HTTP protocol. If these two guys speak different protocols, they will not be able to communicate with each other. They will not be able to understand each other. And the final consideration, which we hinted last time, is the flow and congestion control. That means that if you again consider the example of road network, you don't want to push too much traffic on this road network. Otherwise, the roads will get congested. So you want to make sure that congestion is not happening. You need to make sure that you police the traffic somehow. Okay? So you need to make sure that you do a rate control. You do a rate control of the data that you are pushing onto the network. Okay, so that's those are the main design consideration, and obviously, you know, each of those is a very broad, big topic in networking systems, and many subtopics underneath those. We will learn some of those as we progress in the course. So why do we study the internet? This course is about computer networks, which is a very generic thing. Internet is an example of a computer network, but it is the most important computer network which is visible to us, which we use every day. So why we study the internet? Our focus in the course would be primarily on the internet, not generic computer networks. There can be computer networks which are different from the internet. घर में किसी ने अपना एक network अलग से बनाया हो. So what we are going to do is we are going to focus mostly on the internet, and we will point out the differences with other networks if there are any. Okay. So the reason that we study the internet is because it is transforming everything. Anything related to business, relationship, learning, education, law, governing, and telemedicine, e-health, curing of diseases, everything that we think of today is being done over the internet. You guys might have realized in the last few months that most of us are staying at home. Lots and lots of people are ordering groceries over the internet. We have applications for that. So that's a very common use case that we are all able to see and witness. So the internet is also a big business. You know, companies like Cisco, Juniper, Broadcom, and AT&T, Akamai, Huawei, these are huge companies and huge industry, you know, in terms of monetary value and in terms of impact as well. Similarly, networking is central to many technology companies: Google, Facebook, Microsoft, HP, Dell. All of these companies, they use internet one way or the other. So if you take the example of Google and Facebook, they probably will not exist if you don't have the internet. These companies exist because of the internet. Okay, so also internet research has a very broad impact. It's very fascinating to see that the internet started as a research experiment. Research agency in the US, they performed an experiment, in fact, coming from the Defense Department, and they started this experiment, and this experiment just proliferated, and we have now nodes everywhere in the world. You know, IoT devices are everywhere in the world. So internet research, networking systems research has a very broad, very deep impact. 4 out of 10 most cited authors in computer science and engineering are from the networking area or networking systems area. Many successful companies that we know of have emerged from here. So some of the defining characteristics of the internet. We will just talk about some of the defining characteristics. One is it's a federated system. So the internet, it interconnects different networks. We gave this example last time. these devices here, these guys here, these guys here, these are end devices. So these are some of the end devices, these red circles that I'm showing you here. And these end devices are spread across the internet. They want to talk to each other. Each of these yellow guys is an ISP, and this is an ISP. This PTCL is an ISP, which will provide service to many of these end users, many of the end devices. So these end devices will be connected not directly to each other, but through their internet service providers to another service provider to the end device. And we gave a very detailed example last time. If you did not attend the lecture last time, you please go ahead and watch the first lecture video, which is available in the cloud. We have provided the link for that already on Piazza. Again, if somebody did not attend the last lecture, we will be using Piazza and LMS for course management. So any questions that you have about the course, you can ask on Piazza, and any sort of handouts that we make available to the class will be done through LMS. You can also submit your homeworks on LMS. We'll talk about that when the first homework is given out. Okay, so now you see that these end devices are connected to the ISPs, and lots and lots of ISPs, tens of thousands of ISPs in the world. They are all interconnected to each other. Maybe not directly. AT&T and Verizon are probably connected to each other directly. These are very big networks. But PTCL is not directly connected to Verizon. PTCL will be connected to somebody else, maybe Singapore Telecom, which will connect it to AT&T and Verizon, or maybe PTCL is connected to another ISP, which is PCCW, another large service provider, and then PCCW will be connected to AT&T. But at the end of the day, just understand that we will have some sort of connectivity. Maybe I'm not directly connected to you, but through some of the intermediate links and switches. Very important, links and switches. Through these links and switches, I will be connected to anyone in the world, a connection between a communication between myself, between my device and another device in the US will probably traverse through a very large number of links and switches in sequence. And then my data will reach the destination. So this federated system uses one common protocol. It's called the Internet Protocol. And this is the protocol which is responsible for all the machines on the internet to talk to each other. Every protocol will require an address. Every protocol will require an address. And for the case of Internet Protocol, the address that we have is the IP address. It's a 32-bit number, as we explained, and we will be using IP address to communicate with, these devices will be using IP addresses to communicate with each other. Now, we also have addresses which are different from the IP addresses. We'll talk about those addresses as we progress. One simple example, if I can quote right now, is if you go to http://www.cnn.com, that www.cnn.com is also like sort of an address. It's also an address. You can use that address to reach cnn.com. Similarly, if you go to www.bbc.co.uk, that's also an address. I understand that. Okay. So that's also an address. That's an address at the HTTP level. We use the HTTP protocol to connect to these websites, and that's the HTTP protocol's address. Okay. At the Internet Protocol level, we have these other addresses, and as you might have guessed, these addresses will be translatable to each other. So www.cnn.com will get translated to an IP address. When I type www.cnn.com in my web browser, although I don't see it, my web browser behind the scenes, it will go ahead and translate that www.cnn.com into its equivalent IP address. Once it gets the IP address, which I don't see, but the browser have received it somehow. We will explain that process. It's called the DNS process. Once the IP address is available to the web browser, then the web browser can send a connection request to the web server at that particular IP address. That communication will be happening at the internet protocol layer. So we'll talk about layering today in some more detail, or maybe in the next lecture as well. So internet is a federated system, and interoperability is the internet's most important goal. What do we mean by interoperability? Means all the devices are able to talk to each other, are interoperable. Similarly, routers, they can talk to each other. Cisco can make a router, Huawei can make a router, my network can use any of these devices, one made by Cisco, one made by Huawei, one made by Juniper, one made by ZTE, and all of these devices together make my network, and the network still functions smoothly, irrespective of the fact that these devices have been manufactured by a variety of vendors, which means that all of these vendors need to make their devices such that these devices are able to talk to each other. That means they are interoperable with each other. This also leads to constant tussle between the businesses and technical factors. What we mean by that is that competing ISPs, they must cooperate to serve their customers. So let's say in a region you have two ISPs, one ISP A, one ISP is B. ISP A has some customers, ISP B has some other customers. Okay. Now we would like all the customers to be able to talk to each other irrespective of who their provider is. Agar ISP A mera provider hai, I don't want to be just confined to the customers of ISP A. I would like to be able to talk to all the customers of ISP A as well as all the customers of ISP B. That is only possible when ISP A and ISP B, they provide connectivity with each other. They are competing with each other, but they must cooperate to serve their own customers. Okay, so that's how there is a constant tussle between these businesses and technical factors. The scale of the internet is tremendous. Almost half or more than half of the world population, is on the internet. 4.6 billion users. Maybe a little bit more than that. You know, this is the statistics I gathered a few days ago. 1.2 billion online website. This is also maybe a little bit older. So now maybe we have another 10-20% added to this. 210 billion emails sent per day. Once again, this would probably a lot more than that. More than 2 billion smartphones, now probably close to 2.5 billion smartphones. 2+ billion Facebook monthly active users. Wow, 400 hours of video uploaded to YouTube every minute. This statistics is a couple of years old. Now it's probably, you know, double that, especially in the pandemic days. It's probably maybe double or triple of this bandwidth. Meeting. So switches that move 300 terabits per second. We have these kind of switches which move data at a very tremendous speed. Links that carry 100 gigabit per second, and these days 1 terabit per second is also going to be available. So there is also an enormous diversity and dynamic range in the internet. Communication latency can be microseconds to seconds. You can have networks, you can have links where the latency between when sending a piece of data and being received at the other end, the latency between these two events can be in microseconds, or it could be in seconds. Similarly, the bandwidth can range from 1 kilobit per second, very low bandwidth, to very high bandwidth, 100 gigabits per second. The packet loss can also be, you know, close to zero on the optical fiber network, to close to very high, 80-90% on some of the really poor wireless networks. You might have noticed, you know, very high packet loss on when you are on campus, sometimes on the Wi-Fi network. So packet loss could be very, very high, hampering the communication. You are unable to connect or being logged out repeatedly. So somebody has a question. Can you define bandwidth? So we will have a precise definition of bandwidth, but bandwidth really means that how much data can you push? How much data can you push in a given time? So when we say 1 kilobits per second, that means in 1 second, I can push 1 kilobits of data, which means 1000 bits of data. So a link on which I can send a data at 1 kilobit per second, that means that link is capable of accepting data or delivering data at 1 kilobits per second. In 1 second, I can push 1000 bits into that link. And in 1 second, I can extract 1000 bits out of that link. Similarly, for a 100 gigabit per second link, you can push 10 to the power 7. No, not 10 to the power 7. 100 gigabits is 10 to the power 11. 10 to the power 11 bits in 1 second. 10 to the power 11 bits per second. So so bandwidth is basically how much data can you push inside the link or extract from that link in one fraction of time, in 1 unit of time. Okay. If there are any more questions, you can either type those in the chat window, or you can also raise your hand. Any questions at this point? Okay, we will move forward. No more questions here. Similarly, there is huge diversity in the technology. We have optical technology, we have wireless technologies, we can have satellite links, we can have copper cables or coaxial cable. All of these are various different technologies over which the data can flow. Similarly, we can have a diversity in the endpoint devices. Devices can be as small as IoT devices, very, very small IoT devices or sensors. And then you can have cell phones. And then you can have, server centers or data centers, which are really, really huge. A typical data center in a big content provider can have few 100,000 machines. It's very normal for them to have that kind of data center, that big data center. And then we also have a variety of applications: Zoom, Skype, live video, gaming, remote medicine, lots and lots of applications. And similarly, you can also have a variety of users on the internet. So what we are talking about here is diversity on the internet in everything. You can have users which are governing or governed, or operators, ISPs, selfish users, malicious users. You can have naive, savvy users, embarrassed, paranoid. It's all kinds of users you can have on the internet. The internet has gone through a constant evolution. So somebody has asked the question, can you repeat what is packet loss? Packet loss is basically, I will describe packet loss in precise terms when we progress in the next chapters. But for now, what would suffice is that if I send a packet from one device to another device, if that packet does not reach the other device because it just got dropped in the middle, maybe it reached some of the intermediate switch. Remember, we have links and switches in between any two communicating devices. So somewhere in the middle, there is a switch which malfunctions and it drops the packet. That happens all the time. If it drops the packet, maybe because it is unable to handle too much data traffic which is coming to that switch from all over the place. So the packet will get dropped, it will not reach the destination, and it would be a packet loss. Another kind of loss will happen when the packet does reach the destination. So packet does reach the destination, but it is not correct, which means some of the bits within the packet are flipped. How would that happen? Again, that might happen when the signals are very low, links are noisy. You can get noise added to the data. And remember, these data bits, zeros and ones, they are sent in the form of electrical pulses, and these electrical pulses can get impacted by the electrical noise in the wires or in the cables, or in, you know, if you're sending optical signals, you can have an attenuation of the optical signal. So it is entirely possible that a bit that you send as one, it get flipped and is received as zero, which means that packet will get received, but one or more of the bits will be flipped. Suhaib, you have a question? Please go ahead and ask.
Yes, sir. So my question is that you are saying that sometime packet data it gets lost. Sir, तो वो data जाता किधर है? कहीं वो किसी और packet data में वो mix हो जाता है या like
हाँ,
where does it go?
नहीं जाता जाता किधर नहीं है. So when the packet gets dropped, that means it signals, you will just forget about that data. That means you know, think about a file that you have stored on your machine. If you delete that file, where does that go? ये कोई फिजिकल उस तरह की चीज नहीं है कि कोई हमारे पास कोई कैंडी है या कोई चीज है जिसको हम खाएं, अगर नहीं खाया तो वो कहीं तो जाएगी, वो उस तरह की चीज नहीं है. So it's equivalent to the data is equivalent to the file that you have stored on your computer. वो भी डेटा की शक्ल में सेव हुई है, ones and zeros. You erase that means it's just gone. It does not exist anymore. That data doesn't exist anymore. So packets are also the same thing. So when it gets dropped, that means it is not forwarded. It doesn't go anywhere. Okay. So internet has evolved constantly and at a very fast pace. 1970s, which is, you know, 4 or 5 decades ago, not too long in the, if you consider the human history. So it's only 4 to 5 decades ago. In the 1970s to today, it's 40-50 years, we have gone from 56 kilobit per second links, which we used to call backbone links. We still call backbone links, but those backbone links have now become 100 plus gigabits per second links. Very fast, very fast. And you can see that going from 50 kilobit per second to 100 gigabits per second, what is the factor here? Huge factor. So that's very fast today. And again, in 1970s, we had less than 100 computers, a small number of sites in the US. That's it. That's the total number of computers on the internet at that time. Now you probably have 100 devices on this floor on which I am sitting. इसी फ्लोर के ऊपर जो है वो 100 से ज्यादा devices connected होंगे. Now, throughout the world, there are more than 5 billion devices all over the globe. Once again, this number is probably now inflated by another 10, 20, 30%. So huge expansion that we have seen in a relatively short period of time. Earlier applications were email and telnet and file transfer. Those were the killer applications of the time. But now millions of apps, you know, App Store is full of applications. Your Android store would be full of applications which are installed per day. Lots and lots of applications that we see. This application that we are using for communication, Zoom application or Skype or instant messengers, you know, used for communication. So many applications which are available to us today. Again, this is an evolution, enormous growth in the applications. Okay, the internet. Another defining characteristic of the internet is that it also has an asynchronous operation. What do we mean by that? Oh, somebody has asked the question, what are the reasons of increase in the speed? The reason for increase in the speed is that previously we were not able to send the data fast. If you wanted to send the data fast, there were physical limitations. If you wanted to send the data faster, the error rates will increase, the bit error rates will increase. The bits that I am going to send from one point to another point, there is a chance, there is a probability that that bit will get flipped, as I explained, because of electrical noise. So improvement in electronics and improvement in devices, improvement in communication theory has led to this enormous growth in speed. I hope that answers the question. So the internet operation is asynchronous. Although, but it seems that what I'm talking here, you guys are listening right at the same time, but that's actually not true. There is a slight delay. There is a slight delay. What I'm talking here, after some delay, this audio that I'm producing, this is being captured by the microphone on this device, on this laptop, being digitized, and that digitized voice is contained in packets, and these packets are coming to you, and you are listening to those packets, the voice in those packets, by converting that audio again, making a digital signal, and then converting it to analog, and then feeding it to your loudspeaker or whatever speaker you are using on phone or on your laptop or your desktop. Okay, so so what I'm talking right now, it reaches you, but it reaches you with a slight delay, with a small delay, and that delay uh, is it can be optimized, but there is a fundamental constraint, and that fundamental constraint is the speed of light. We know that light travels very fast, 3 into 10 to the power 8 meters per second. That's a lot and lot of meters covered in 1 second. But this is still not infinite. The speed of light is finite. So consider, for example, how many cycles does your 2.8 gigahertz CPU, most of the CPUs that we see today are in that range, 2 gigahertz, 3 gigahertz. Um, you know, if you have a CPU which is running at 2.8 gigahertz, how many cycles that CPU would execute before it can possibly get a response against a message it sends to a server in Karachi. So I'm sitting in Lahore, I send something in Karachi, and then it comes back to me. In that time, how many cycles your CPU has executed? So in order to get the answer to this, let me launch a poll. And you can probably answer that. Okay. Maybe you guys can see the poll on your screen. So try to answer that. You send a message, Lahore to Karachi and back, how many cycles your CPU will execute in the meantime? We have one answer only in 18 seconds. We can't wait for too long. Just answer that. And there is no right or wrong answer. Just what's your gut feeling? Whatever your gut feeling says, just try to answer that. So 23 out of 29 we have received, 26 out of 29. And I'm going to end the poll. If you have an answer, just attempt it now. Okay, so I'm going to share the results now. I have finished the poll, and the results is 7% of the students think that it will take less than 100 cycles. I sent a signal from Lahore to Karachi and it comes back at the speed of light, which is extremely fast. In that time, my CPU, which is running at about 2.8 gigahertz, is executing some cycles. 30% students think that the number of cycles between 100 and 1000. 26% think that it's between 1,000 and a million cycles. भाई लाहौर से कराची भेजने वापस आना है, स्पीड ऑफ लाइट पे आना है, हमने ट्रेन पे नहीं जाना, हमने स्पीड ऑफ लाइट पे वापस आना है. But somebody is saying that you can get between 1,000 a million cycles, and there are some people who are saying, 37% of the people who are saying that there could be more than a million cycles in the meantime. So let's take a look. What is the correct answer? Let's try to find it. Okay. So I will stop the poll here. So for that, in order to answer this question, we will need we will need to know what is the distance between Lahore and Karachi. Okay, and for that we can assume, I think, this is probably a reasonable estimate, 1225 kilometer. I think I got this number from Google Maps. Maybe it's a little bit overestimated, underestimated, but doesn't matter. It would be in the same ballpark, about 1200 kilometers, 1300 kilometers. Okay, so traveling at 3 into 10 to the power 8 meter per second. This is the speed of light. This is the speed of light. This is the speed of light. How much time does it take to cover 1225 kilometers? It will take 4.083 milliseconds for a signal traveling at speed of light to go from Lahore to Karachi and then back to Lahore. Obviously, then we need to multiply with the 2. Total would be 8.16 milliseconds. In 8.16 milliseconds, let's see what has happened in my machine. Computer mein kya ho gaya? So we have this 2.8 gigahertz CPU, which means 2.8 gigahertz, so many cycles in 1 second. In 1 millisecond, how many cycles? Just multiplied by that, 8.166 milliseconds. We have 22 million cycles. देखें यहाँ से लाहौर से कराची को चीज भेजी with the speed of light, and it comes back. Meanwhile, your CPU has executed 22 million cycles. 22 million cycles. That's enormous. You can do a lot of things in 22 million cycles. Yeah. So what the result is, we conclude that the communication feedback is very dated, is very old. You have done a lot. Your CPU has executed 22 million cycles in the time that somebody has sent a signal from Lahore to Karachi and it comes back at the speed of light. Even though it is coming and going at the speed of light, still you have very stale information that came back from Karachi. So if somebody from Karachi gave you feedback, that feedback will be very, very old as far as the electronics is concerned. Okay. Now, another defining characteristic of the internet is that it is prone to failure. And we see that very often, especially when you are on campus, on LUMS network, trying to register for the courses. So to send a message, all components along a path must function correctly. So what we mean by that if I am sitting here, I'm connected to this Wi-Fi access point, this is connected to a switch, on this floor, then the switch in the basement, switch in the IST department, another switch in the ISP, and maybe many switches between myself and you, and these switches are connected through links. Now there are many components along the path between my machine and your device, many paths between my machine and your device. Okay, all of those links, all of those switches must be functioning properly, must be functioning correctly for the communication to happen. If I'm sending a packet to you, the packet will get through to you if everything, all the links, all the switches between me and you are working correctly. Okay. Now, and when we say components, means all the software, modems, wireless access points, firewalls, links, everything which is in between must be functioning correctly. We don't know anything about firewalls or details of the network interface cards. We'll talk about that in this course in some detail. And of course, we'll talk about switches in great detail. Wireless access point, we'll talk about in some detail. Modem, we are not going to talk about modems. It's an old technology. Again, has been replaced by newer items, newer switches. Software, we'll talk about that. Okay. And again, we are talking about human operators. If there are some human operators, we want them to function properly as well. Okay. Now, if you consider 50 components, each of which works correctly 99% of the time, yeah, that means if there are 50 components, links and switches between me and somebody else that I am communicating with, and each of those functions properly 99% of the time, then there is a almost 40% chance that communication will fail. wow, this is amazing. This is amazing. Each of the function is functioning properly 99% of the time. 99% of the time. Lekin the communication will fail 40% probability के साथ communication fail हो जाएगी. Why is that true? Because there are just too many components, 50 components. Although each of those individually is 99% efficient, working correctly 99% of the time. But that 1% chance, 1% probability that they will fail across 50 components, the chances that someone will fail, the chances that someone will fail are pretty high. And that pretty high is 40%. That's a pretty big number, pretty big number. So also recall that internet is prone to failure. Also recall that the scale of the internet is very, very large. There is lots and lots of components. This probability is 40% or as high as 40% because we have too many components here. If there were only 2 components, the probability would be very close to 98%, 99%. But since we have 50 components, which is a large number, the chances that at least one of these guys will fail will be close to 40%. So you recall that the scale of the internet is large. There are lots of components that the probability that something will fail somewhere is very, very high, okay? So if we take the example of a typical data center, which has a few 100,000 machines, every data center, we know that, when we send a search request to Google, it almost always gives you the response. It's very rarely that it will fail, very rarely. But imagine this Google servers, which are performing the search, they are hosted in a data center. They are hosted in a data center. In that data center, when your request reaches that data center, at least one machine would be failing. It is very, very likely that one of the machine or maybe more than one of the machines will be failing because there are few 100,000 machines in there. Okay? Since those machines will be failing, but you will still get the response. It's because they have designed the data center such that even if something is failing, you are still able to get the response from those components which are not failed. Plus recall that the internet operation is asynchronous and it will take very long time to hear the bad news. So let's say there is a feedback mechanism. I try to send some packet to somebody else in the US, somewhere in the middle, maybe around Europe, the packet gets dropped or packet gets corrupted. So that feedback might come back to me that please send the packet again because the earlier packet that you've sent has been dropped. So please send the packet again. That's a very courteous thing to do. If you are sending something and it gets dropped, you would want to send it again. Okay? Imagine sending a large file to the destination, and that large file is divided into small packets. Each of those packets are going through, and there are millions of packets in that file. All the packets go through except for one packet. The other guy is not going to be able to create the file. उसके पास तो file बनेगी नहीं क्योंकि एक बीच में से packet missing है. Now, so that means if the packets get dropped, you would like to send the packet to the other side because you want to make sure that at least in this case, the communication is reliable. In order to ensure reliability, you need to make sure that if a packet gets dropped or even if a packet gets corrupted, when I say corrupted, that means some of the bits are flipped in the packet, then you resend the packet to the other end. But you will only resend if you know that the packet has dropped. And how will you find out that the packet has dropped? You will find out because you will hear about the bad news that the packet has dropped, please send it again. But in order to hear that bad news, it might take a very long time. We saw the example, 22 million cycles will be executed by your CPU even if you hear something from Karachi, as close as Karachi, because of the fundamental limitation of the speed of light. Okay. So, so internet is an engineered system, is constrained by limits of available technology, bandwidths, switch port counts, bit error rates, cost, and so on and so forth. So recap, of what we have talked about, the internet is a federated system, a system in which all the hosts are able to communicate with each other, connected with each other of enormous scale. It has a dynamic range, lots and lots of diversity, lot different kind of users, different kind of technologies, different kind of devices. It's constantly evolving. We saw that in 1970s, it looked something else. Today, it looks something else. Even 20 years ago, 15 years ago, it looked something else. Even think about 10 years ago, 15 years ago. Netflix wasn't that popular. Netflix only has become popular in the last 10 years. In Pakistan, I think we have it only for the past few years. Um, it's asynchronous in operation, and it is also failure prone, constrained by what's practical to the engineer. So what we know about the internet is that the early internet pioneers, they came up with a solution that was successful beyond all imagination. They have no idea in the 1970s that it will become such an enormous thing. उन्होंने तो 2 nodes लगा दी थी, 3 nodes लगा दी थी. There were only a couple of nodes, and then this experiment just take the snowball effect, and it has become so large. So several enduring architectural principles and practices emerged from that. As the internet started evolving, the number of devices on the internet started increasing. We had to had some sort of architectural principles and practices. Otherwise, we would not have been able to scale. ये scale हम बढ़ा ही नहीं सकते थे अगर हम कुछ principles and practices को follow ना करते. And those principles and practices are the topic of this course. And these architectural principles are decentralization. Decentralization. What does that mean? That means कि ऐसा नहीं है कि कोई एक बंदा बैठ के जो है वो इंटरनेट चला रहा है. There is no one body which is sitting and controlling the internet. It is highly decentralized, highly decentralized. The communication that is happening between us right now, assuming all of you are sitting in Pakistan, if all of you are sitting in Pakistan, then this communication is just confined between us. It's confined between, even on the network, the packets are traversing PTCL's network and Nayatel's network and Cybernet's network and LUM's network, whatever ISP you are using, their network. But this conversation is just limited. Nobody outside Pakistan is able to see this conversation. These packets are just confined to these networks. Similarly, a conversation happening in Europe, it's just limited to that. So it's a decentralized operation. There is no centralization. ऐसा नहीं है एक जगह पे सब पैकेट एक जगह जाएंगे और फिर वहां से डेस्टिनेशन पे जाएंगे. So architectural principles include the decentralization, also includes packets. This is very important. This is extremely, extremely important. The voice that I'm producing, it is digitized. It's a sequence of ones and zeros. Until I stop, it would be a continuous sequence of ones and zeros. Similarly, a word file, a large word file would be a continuous sequence of ones and zeros stored on your machine. You can't send all of those ones and zeros simultaneously. एक दम से उठा के एक पैकेट में नहीं भेज देंगे, एक डेटा चंक के तौर पे नहीं भेजेंगे. I will need to divide this big chunk of data. My audio, which is being digitized, a big chunk of data has to be packetized. ये पैकेट होके आपके पास आ रहे हैं. अगर ऐसा ना होता तो फिर क्या होता? 1.25 घंटे का एक लेक्चर, all the bits here and all the bits in one go will come to you. You will have to wait for 1 hour 15 minutes, and then this will come to you and you will decode those. Very, 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 very inefficient. Very inefficient. Similarly, for Word file, packets start going. You start downloading as you progress. You start downloading files as the packet comes to you. So these big chunks of data are always divided into these smaller chunks of data of the order of 1 kilobyte. 1 kilobyte. 1 kilobyte is still large. I mean, 8,000 bits. 1 kilobyte is 8,000 bits. But that's the typical size of the packet on the internet. So we have these 1 kilobyte chunks of data which come to us. One after the other. All of these packets, they come to us. Okay? Some might get dropped. They will get retransmitted. If they don't get dropped, then we will have all the packets. If I am sending a file to you, if I'm sending a Word file to you, which is packetized, and these packets are coming to you one after the other, I require that none of the packets are dropped. Why? Because I want to replicate that file at the other end. If I'm talking in my audio, if one packet gets dropped, it's okay. I'm not going to be bothered about sending it again. Why is that? Can somebody answer that? Please raise your hand if you can answer that. So we consider two examples: sending a file in which I want all the packets to go from source to destination. If one packet gets dropped, it must be retransmitted. It must be sent again. But when I'm talking, the audio signal, the packets which contain my audio, if one packet gets dropped, maybe I will not be bothered about sending it again. I will just say, okay, theek hai, gaya to gaya. I'm not going to send that packet again. Why is that? Can somebody answer that? If you can, please raise your hand. Please raise your hand. So somebody has responded. I'm not going to read that answer until somebody answers. Hamza. Hamza,
Ji
please
sir,
go ahead.
Maybe because the data that is lost isn't as significant as compared to the entire data that is being received. So when you're talking about voice, तो अगर आपकी voice के अंदर से एक bit drop हो जाता है तो maximum से distortion ही आएगी. कोई इतनी communication factor तो नहीं आएगा.
Good, Hamza. That's a correct answer. And Aisha Rafi has also answered the same, that the audio will still make sense without that one packet, because this one packet is, out of these millions of packets that are that I am sending, one packet is nothing. If it is lost, it is lost. And there is no point in sending it again anyways. Why? Because that packet belongs to the voice that you have already listened. दोबारा से भेजने का उसका फायदा ही कोई नहीं है, पहले ही सुन लिया आपने. But think about it. If I am sending an MP3 file to you, that's also audio. If I'm sending an MP3 file to you, I would want that MP3 file to be exactly replicated at your end. In that case, I cannot afford losing a packet. If I lose a packet, I must send that packet again. Okay. I hope that makes sense. If that makes sense, please click on yes. वो नीचे yes आपके पास होगा, participants वाली list में होगा. Makes sense to some people. Doesn't make sense to other people. Oh. Okay. Okay, that's great. Lots of yes. Okay, so I'm going to clear these yeses now. So architectural principles, decentralization, and then we have packets. Everyone understands that, how do we make transmissions, how we send data over the internet by dividing large chunks of data into smaller packets, okay. And then another important thing is about statistical multiplexing. That's the, one of the holy grails of internet communication. The reason that internet communication is so cheap as compared to, let's say, phone communication. Your WhatsApp call is free, and if you call over a telephone network, that is not free, and it actually has become much cheaper now. 20 years ago, it used to be, probably 10 times, 50 times more expensive. And the reason that that we have internet access so inexpensive is because of this guy, statistical multiplexing. That means that internet consists of a lot of resources, switches and links. They cost something. Okay. If these links and switches are dedicated to a connection, then the owners of those connections, the holders of that connection will need to pay for that. Okay. But that doesn't happen. We don't pay for switches. We don't pay for links. Somebody else, and service provider pays for switches, service provider pays for links. And what we mean by statistical multiplexing is that sometimes I need to use the network, I just use the network. when I'm not using the network, somebody else can use the same resources. This is like the time sharing principle. Um, you rent a house, a vacation house, um, with few other families, and according to your schedules, you can just go and use that house, that vacation house, and that's how you benefit. Otherwise, all of those families would have to buy a house for themselves. Instead of that, they pull in the money, buy a house, and then what they do is they can use that house whenever they need, as long as there is no conflict. As long as there is no conflict, you need to make sure that the schedules fit with each other. So if I'm using the house, then nobody else is allowed to use that house. Statistical multiplexing has the same principle. So in the case of statistical multiplexing, the network resources, which are the links and the switches, these are used by those people who need it. Those who don't need it, um, they can just sit free. So I will give you another example. So let's say you go to www.cnn.com. You type that address and you hit enter. Your browser first translates cnn.com into its equivalent IP address, and then makes a request to that IP address, an HTTP request to that IP address, that www.cnn.com, please give me the file corresponding to that. वो एक फाइल जो है आपके ब्राउजर के पास आ जाती है, and your browser displays that. It takes probably 1 second, maybe 2 seconds, maybe 3 seconds. About that. 3 सेकंड में वो फाइल आपके पास आ गई है, and then your browser will display that file that it has received. Okay. Now you will probably take 4 or 5 minutes to read through that file, through that web page. Maybe browsing looking at some of the news, looking at some of the pictures, etc. So in those 5 minutes, when you are not using the network, somebody else can use the network. So this is the basis of statistical multiplexing. We will talk a lot more about statistical multiplexing later on. The architectural principle of internet is that it's a best effort service. See, we talked about packets getting dropped, and packets getting corrupted. So it's the best effort service means that it will not guarantee that the packet will get through. Sometimes the packet will get dropped. What you can do is send those packets again. Best effort service is never a promised service. कोई चीज promise नहीं कर रहे आपसे. ठीक है? We will make an effort. We'll make a best effort. The packet will get through. But if one packet gets lost once in a while, tough luck. You are on your own. And when somebody says that you are on your own, you have to make sure that you have a backup plan. And your backup plan is that send that packet again, please. So best effort service is provided by the internet, but it is your application. Which needs to make sure that if your application is using the internet and a packet gets dropped and your application learns that the packet has gotten dropped, then the application sends that packet again. उसको दोबारा भेज देना चाहिए. ठीक है? So this is one of the core architectural principle of the internet. See, we could have provided guaranteed service. But it would have made the network so expensive, so complex, कि हमने decide किया at the time of designing that it would provide only the best effort service. It is not going to provide a guaranteed service. ठीक है? Now you might ask this question कि हम फाइल जब भेजते हैं वो तो पूरी की पूरी चली जाती है. Well, पूरी चली जाती है. It gets divided into packets. Some packets probably also get dropped. You don't see that. Your application doesn't see that. Okay? But some of the packets which would have gotten dropped, they get retransmitted. वो भी behind the scenes होता है. वो आपको नहीं पता चला. वो behind the scenes जो है वो retransmit हो गए हैं, and your application is happy that the entire set of packets that it wanted to send, they have gone through. Okay. And internet also uses the end-to-end design principle, which means one application on my machine is talking to another application on the other machine. There is an end-to-end design principle. We'll talk about that in some detail. Now, this is a important time to mention that on a particular machine, on a particular device, on a particular laptop, on a particular desktop, um, there will be many network applications running. You can have instant messenger, you can have web browser, you can have a different web browser, you can have Firefox and Safari and Internet Explorer running at the same time. These are all network devices. You can have Zoom, which is also a network application. You can also have Skype, which is also a network application, all running at the same time. You can also have a file transfer applications being run on your machine. Again, a network application. You can have many different network applications running simultaneously on your machine. Simultaneously on your machine. The data which comes to your machine, from all the other places, or these multiple applications which are sending the data out of your network, this is going through one network interface. एक ही network interface से वो जा रहा है. And somehow these applications are able to distinguish ये data मेरे लिए, ये data मेरे लिए, ये data मेरे लिए. So for example, if you are running 5 network applications on your machine, all the data that others are sending to you are being sent to you through one network device, which is your network interface card or wireless interface card. Okay. Once the data gets into your machine, somebody will demultiplex that. Somebody will send it to specific application. Chat का data chat वाली application में चला जाएगा. File transfer का data file transfer की application में चला जाएगा. Audio का data Skype का data Skype वाली application में, Zoom का Zoom की application में, web browser का web browser की application में. So somebody will be sitting in your machine and will be making these decisions. But we also have is the layered decomposition, and this is connected with what we have just described, that the data which comes to you comes through one single physical interface, and then it gets to those 5 network applications that you are running. How it gets delivered to specific application, a layer sitting in your machine will decide, a piece of software sitting in your machine will decide, इसको इस application को दे दो, इसको इस application को दे दो, इसको इस application को दे दो. You don't have to write that piece of software. That piece of software is already written for you, and that piece of application is called the transport layer. If you have heard the name TCP, then TCP is a protocol which is used at the transport layer. That transport layer will decide कि कौन सी एप्लीकेशन, Zoom को पास ये पैकेट जाना चाहिए, या ब्राउजर के पास ये पैकेट जाना चाहिए, या टेक्स्ट मैसेज अगर हो रहा है या इंटरनेट मैसेंजर के ऊपर कहीं बात हो रही है तो उसके पास ये मैसेज जाना चाहिए. So this will be decided by the transport layer, and the transport layer uses the one of the most prominent protocols which is used at the transport layer is called TCP. Another protocol which is used at the transport layer is the UDP. Now, what do we mean by these layers? Last time we gave this example. Okay, you have an application layer, your web browser or Zoom application. These are applications. So they fall in the application layer. And then you have this physical wire or wireless connection, which is the physical layer. These are the 2 extreme layers on your networking stack. किसी ने ये physical layer design की है, किसी ने ये applications का code write किया. There are 3 layers in between as well, जिसमें से एक transport layer है, जिसने ये decide करना है कि कौन सी application के पास data जाएगा. ठीक है? We will talk more about that in the next lectures. So another layer which exists in the networking stack is called the IP layer, which runs the internet protocol, which makes sure the data on one machine goes to the data on another machine. वो ये नहीं बताएगा इंटरनेट प्रोटोकॉल कि उस मशीन पे कौन सी एप्लीकेशन में जाएगा, वो ट्रांसपोर्ट लेयर बताएगी. बट internet protocol at the network layer, it will tell you which machine on the internet, which IP address on the internet should receive the packets that you are sending. Should receive the packets that you are sending. That is decided by the internet protocol or the network layer. Internet protocol is the protocol which is run on the network layer. And then once it reaches the destination, then the transport layer will decide which application will receive the packet. We will have a lot more discussion on that. अभी कोई question है तो please feel free to ask those. Raise your hand. So network architecture is about thinking more rigorously rather than doing. There is not too much math involved in here. It's just thinking rigorously. More about understanding the trade-offs than running the benchmarks, and more about practicality than optimality. We want to make sure that things work by and large, rather than finding out the most precise optimal operating point. So this course is going to teach you how the internet works, why it works the way it does, some of the guiding principles of the design of the internet, and how to reason through a complicated networking design problem. तो ये कुछ टॉपिक्स हैं, ये हम कवर करेंगे in some detail. Any questions at the moment? कोई और क्वेश्चन है? अगर नहीं होंगे तो फिर हम सेशन खत्म करेंगे. Suhaib bin Mohsen. Suhaib, you have a question?
Yes, sir. Sir, when you were solving that 2.4 gigahertz CPU problem, you used the speed of light as speed constant. So why did you do that?
Why did I do that?
Yes, sir.
What was
Maybe
the
it
question?
Sir, when you were solving that example about the
जी
cycles
जी
वाली के, तो उसके
जी
अंदर
जी
आपने speed of light को use किया था as a speed constant. तो
जी जी.
मतलब क्या पैकेट्स हमेशा speed of light से मूव करते हैं, या did you do because वो best case है, best
Good
case
question.
scenario?
Good questions. The packets, the fastest they can move is the speed of light. उससे थोड़ा slow हो सकती हैं. So whenever you send the electrical signals, they move with a speed which is less than the speed of light. It's a big fraction of the speed of light. You would want this speed to be as fast as possible. Obviously, it would not exceed the speed of light. So maybe 90% or 80% of the speed of light, depending upon what medium they are traveling in. So 90% is a decent is a typical speed of transmission. 90% of the speed of light, which would be 2.7 into 10 to the power 8 meters per second. 2.7 into 10 to the power 8 meters per second. This is 90% of the speed of light, and many of the electrical signals will be propagating at this speed. In the wireless, they will propagate at close to the speed of light, maybe a little bit more than 90%. But again, it depends upon various factors, the medium that they are traversing in. So if there is humidity, maybe transmission speed will the propagation speed will be different. So in the next lecture, we'll talk about this propagation in some more detail, and we will talk about another delay, which is called the transmission delay, and we'll try to find out the difference between the two. But again, nothing can move more than the speed of light, and electrical signals will propagate at roughly the speed of light, slightly lower than that. I hope that answers your question. Huh?
Yes, sir.
जी और किसी का क्वेश्चन? No more questions? So if there are no more questions, then I'm going to stop this session now. All right, see you on Wednesday at 9 a.m. Okay, we'll have the video available on the Piazza website. Khuda Hafiz.
Sir, can we also upload lecture slides?
Lecture sites?
Yes, sir. So first
You mean
lecture के नहीं होगा?
the first lecture. Oh, lecture slides.
Yes, sir. Lecture
Okay,
slides.
I will upload the lecture slides. No worries. I will
Thank
do
you,
that right now.
Thank you.
Okay. Any other question? All right. Khuda Hafiz.